today is going to be lecture 5 for circuit theory, and what we have done so far is as follows. We have done a basic introduction to circuit components, then we have done some amount of graph theory, incidence matrix, etc. Then we have proved Telegans theorem, right, and then we have done mesh method and node voltage method, right. And in the previous class we have also proved the reciprocity theorem based on Telegans theorem, right. So, reciprocity theorem had two parts. Part 1 was I apply a voltage source at port 1, measure the current at port 2. I apply the same voltage source at port 2, I will find that I measure the same current at port 1. This was part 1 of the theorem, A and B, right. This is what we proved in class using Telegans theorem. What we did not prove in class was the second part of the reciprocity theorem. The second part states that I apply a current source at port 1 and with a voltmeter I measure V 2, right, and then I apply the same current source at port 2. It turns out I will get the same reading on the voltmeter at port 1. Okay. So, this was your you were supposed to do it, right. So, if you have not done it, do it once, do it, right. It is the same proof as what we did for A and B. You will have to list out all the voltages, all the currents, and then you will have to do the mixed dot products just like this, right. You have to take the voltages from experiment C, currents from experiment D, do the dot product equal to 0, and then voltages from D and currents from C, do the dot product, and that also has to be equal to 0, and therefore, the two are equal to each other, right. And as soon as you do that, all these other terms are going to cancel with each other. These other terms R 1 I R 1 A, I R 1 B, this is going to cancel from both sides, and all you are going to be left with is going to be V 1 V 2 times I 1, right. No, yeah, I 1 times V x is going to be equal to I 1 times V 2, something like that, right, and therefore, V 2 should be equal to V x, V x should be equal to V 2, something like that you will get, and you should be able to prove it is not very difficult. So, please do it, it is practice. Okay. So, before we do the other network theorems, there are many other network theorems. Okay. What we are going to change our gears a little bit, and so far we have been using only resistors in our circuits. When we did mesh method, node method, right. Also when we proved reciprocity, we only used resistors in the circuit. We did not use inductors and capacitors, for example, and mutual inductors. We have so far not analyzed any circuits with L, C and M. Okay. So, we need to rectify that. So, to rectify that, we are going to change tracks a little bit, all right. And the way we are going to do it is as follows. We are going to discuss the sinusoidal steady state. So far we have been working with voltages that have been constant. Okay. What you already know from your class 8, class 9 high school is that if you plug in to the power socket, you will get what? AC, right, the voltage is alternating. Am I right? So, how do we deal with alternating sources? So, that is what we are going to start with. Okay. So, our sources are of this form. All our sources are of this form V naught. V naught is a constant, whatever I write with capital letters is a constant, times cosine of omega t plus phi. You are soon going to realize that EE students, they enormously prefer cosine over sine. Okay. We love cosine, we do not like sine at all. Okay. So, V naught cosine, although sine and cosine, what is the difference? Pi by 2, there is a difference. So, phi is pi by 2, it becomes sine. Okay. Never mind, we do not want to worry about sine at all. In fact, we are not going to write sine, we are only going to write cosine. Now, before we start studying this sinusoidal steady state circuits, we are going to worry about 3 preconditions, that is 3 assumptions. All right. We are going to write down these assumptions before we start the study, because the assumptions are important. You have to sometimes remind yourself that, oh, I assumed that, and therefore, this is not true anymore. Right. So, we have 3 assumptions. Assumption number 1 is that our circuit is excited by many voltage current sources, independent sources. Right. So, all independent sources are oscillating at omega. What do I mean? Omega is fixed, omega is the frequency, or rather here it is not the frequency, it is the angular frequency. So, omega is the angular frequency. This angular frequency is exactly the same for all the sources. In other words, there is no beating. You know what is beating? Huh? There are no beats happening between different sources. They are all at the same frequency. In other words, they are in phase, coherent. Okay? All the sources are in phase. Let us not say in phase, let us say synchronous. All right, and no beats. Between different sources. This is an important assumption, and in real life this assumption fails more times than not, but nevertheless for this study we are going to assume this. Fine. Second assumption that we are going to make is that this V naught cos omega t plus phi, this voltage source, was switched on a long time back, before you were born it was switched on, or a very long time back, okay, at t equal to minus infinity. All right, and it has been going on and on and on ever since. In practicality, in electrical engineering, this minus infinity happened 10 seconds back, 5 seconds back, because time scales in EE are very small. right. We deal with nanoseconds, picoseconds, microseconds, femtoseconds, right. Minus infinity was a few seconds back is minus infinity for us. All right. So, minus infinity was not too far back in time in practical, in all senses of practicality. However, for the sake of the mathematics, we are going to assume that it was at minus infinity that the circuit was set up. Fine. Then assumption number 3, there are no autonomous oscillators inside the circuit. What does this mean? So, for example, you know this circuit, what is this? LC oscillator. What does it do? You put some charge on the capacitor, it gives the charge as a current in the inductor, and then the inductor pushes the charge back onto the capacitor, and then it just keeps energy keeps sloshing back and forth between the inductor and the capacitor, inductor and the capacitor, and it goes on forever and ever and ever by itself, right, without any other input, right. So, my assumption over here in this study is that we are not dealing with such situations, right. There are no such situations where the circuit is going to produce a voltage by itself without any outside input. So, that is not going to happen. Fine. We will see later what this really means if we have time in future, but for now suffice it to say that there are no autonomous circuits that are self sufficient. All right. So, these are my assumptions. In general, these assumptions are not necessarily true, right. In fact, condition number 1 is very hard to satisfy if you have multiple sources. Condition number 2 is easy to satisfy for us, as I said, but nevertheless I have listed it out. Condition number 3 is also not too bad, we can make it is not a terribly difficult thing, right. 1 is very difficult, this, right, you have to be very careful with 1. Lot of times 1 you will violate and things will start beating, and then all of this study is not going to be effective, right. Whatever we are studying, going to study now, right, it relies on these 3 assumptions. Fine, shall we proceed? Okay. So, to start with, we are going to do a little bit of maths, and one of the basic concepts that EE students use is a function called the delta function. Delta of t. So, delta of t is a function such that it is a 2-part definition. So, first part is integral delta of t dt going from minus infinity to plus infinity is equal to 1. Okay, what does this mean? That the area under the curve is equal to 1. Delta of t is a function, some function, the area under the curve is equal to 1. Okay, this is the first part of the definition. The second part of the definition is that delta of t is equal to 0 for all t that is not equal to 0. Okay. What does this mean? Overall, what does this mean? The two clauses together. It must be infinity at 0, because the area under the curve has to be equal to 1. As long as it is not 0, delta of t is equal to 0. So, the function basically looks like this. So, as long as it is not equal to 0, my function is going to be equal to 0, right. Clause number 2, it is going to be equal to 0 throughout, but then the integral under the curve has to be equal to 1, and the only way for that to happen is if I really jump up to something really large at t equal to 0, right. So, we indicate this with an arrow. Fine. So, this is a special function delta of t. This is also called the Dirac delta function. You would have heard of this in physics. Right, but the EE students, they have a special name for this, they call it an impulse. All right. We are going to use these things a lot, right. Throughout your 4 years of EE experience over here, you are going to use this delta function, right, and more all the time. Okay. And therefore, we have a special name for the delta function, we call it an impulse. Okay. Now, also recall that all of our systems are going to be linear and time invariant. Okay. So, recall linear and time invariant. What does linear mean? So, I have a system, right. Suppose my input is x 1 and my output is y 1, input is x 2 and my output is y 2, then what will be the output when my input is x 1 plus x 2? Y 1 plus y 2. This is the definition of a linear system. Agreed? What will be the output if my input is alpha x 1, alpha y 1? Fine. This is the definition of a linear system, homogeneity and superposition. Okay, great. Then quickly, so I am going to write LTI over here. LTI stands for linear and time invariant. All right. Now, what we are going to do is we are going to apply x of t and my output is y of t. Okay. And if I delay the input, if I shift the input by tau, it becomes x of t minus tau. Am I right? Whatever was happening at t equal to tau earlier now happens at t equal to 0. Fine. Let us not call it tau, let us call it t 0, t minus t 0. I shifted by t 0. What will be the output now? Y of t minus t 0, and which property is this? Time invariance. This is the time invariance property. So, if I applied x of t, I got y of t. If I apply x of t minus t naught, then my output is going to be y of t minus t naught. If I do the same experiment t naught seconds later, I will get the same output t naught seconds later. Fine. This is the statement. Okay. So, remember this, these are two different things, they are going to be used. All right. All our circuits are going to be LTI, all our circuits. In this course, all the circuits are going to be LTI. All right. Which components? Resistors, capacitors, inductors, mutual inductance, VCVS, VCCS, CCVS, CCCS, right. These are all linear and time invariant components. We are going to use all these components to make circuits. All our circuits are going to be LTI. Fine. Which is the input, which is the output in our circuit? Input can be a voltage source, output can be any measurement that you do. You can measure any voltage, any current, right, it does not matter. Okay. So, from any source to any output, it is linear and time invariant. All right. Now, what we are going to do is, we are not going to do this X business right now. We are going to apply delta of t to the system. All right. What is delta of t called? Impulse. So, when delta of t is applied to the system is going to respond. All right. That response is called the impulse response. That is what it is called. When I apply delta of t to the system, what do I get? I get the impulse response of that system, and EE students, they write it as h of t. Okay, I do not know what others do, but this is what we do, we write it as h of t. What is the impulse response? The impulse response is a property of the system. Suppose you go to the market and purchase a system, that system has a property, it is h of t, right. Sometimes the shopkeeper will tell you this is h of t, go and do whatever you want with it. All right, now you come back home and you can apply delta of t if you want, you will see h of t. You need not apply delta of t, you can apply other things, right, knowing in mind that had I applied delta of t, I would have got h of t as the response. Okay, this is the idea. Fine. All right, so far so good. Now, what we are going to use? We are going to think of the following. Okay, I have drawn a graph of some function x of t. This is what I would like to apply to the system that I have purchased. Okay, some function with time. Maybe let us pull it down also. Okay, something arbitrary, it does not matter whether it is mathematical or not. Some arbitrary signal I would like to apply to my newly purchased circuit. Okay. This x of t can be broken up into lots and lots of impulses. My claim is that this x of t is as if it is a sum of lots of something times delta of t plus something else times delta of t minus t1 plus this is t1, then t2. Remember what is the shape of delta? It is just a spike, it is just a single point spike. So, the delta is like delta of t, okay, just by the way, this was delta, it is a spike at t equal to 0. What is delta of t minus 1? It is a spike at 1. So, I go all the way to 1 and at 1 there is a spike, fine. What is delta of t minus 5? It is a spike at 5 and so on. What is 5 times delta of t minus 1? It is still a spike. It has now what this spike is going all the way to infinity. Now, that will go to 5 times infinity, does not make sense, no. What changes? The area under the curve becomes 5. Okay. So, if I scale the delta, the area under the curve changes according to the scaling factor. The height is still infinity, I mean infinity times 5 is infinity only. Okay. Great. So, what I am saying over here, ये क्या है? Okay. So, what we are claiming over here is, to start with, think of x of t as this point, this point, this point, all these points. Okay. So, I am saying that it is this height at t equal to 0 times delta t minus 0. Then it is this height times delta t minus 1 plus it is this height times delta t minus 2. Okay. Now, add more and more and more and more of these, right, lots and lots, pack it up, right, so that there is no space, right. Is this okay? Can you imagine lots of these deltas, right, and then we do not do a plus anymore. What do we have to do? An integral, we have to write an integral sign. All right. So, this is my claim. This is okay. Have you understood this? Instead of doing t minus, so I am moving to the point tauth point, right. I am going to tau at t equal to tau. Suppose this is t equal to tau, right. What is the height over here? The height is x of tau, right, and I have to shift the delta over there. So, it becomes delta t minus tau, fine. So, this is the claim that I am making, that x of t is really equal to integral minus infinity to infinity x of tau delta of t minus tau d tau. Agreeable? No problem so far? No problem, good. Because if this is x of tau, x of t, right, what are we doing over here? We have broken up x of t into a series of these impulses, all right. Large number of these impulses. We have said that it is an impulse at this time plus an impulse at this time plus an impulse at this time, and these times are all back to back to back, right. There is no space between them, but nevertheless it is a sum. Okay. And when I have a sum, my linearity property holds, all right. If I apply a sum of two signals to a linear system, then the output is going to be the sum of those two outputs. Now, I have applied an integral, not really a sum, I am applying an integral of many different of a signal, then my output is also going to be similar. Agreed? All right, let us go back. if my input was delta of t, I was calling my output h of t. Fine, right? H of t was called that impulse response and so on. Now, my input is not delta of t anymore. I have come back from the shop and now I am planning to apply x of t, but x of t is a series of deltas like this, right. It is an integral with lots and lots of deltas of different sizes, all right. So, what is going to happen? If this is my input, what is going to be my output? X of tau is just a scaling factor, right. Linearity, the scaling factor remains the same. Yes, h of t minus tau d tau. Fine. Is it okay? So, we have developed something very important. Yeah, you have a question. This first part, this part. Okay. So, what I am suggesting is, let us break up x of t into lots of different small things. So, first this one plus the next one plus the next one, right. Now, let us describe each one of these. Each one of these has a height x of tau, right, and it is being multiplied by delta t minus tau. Why is it delta t minus tau? Because delta t minus tau is what picks, it is the shifted one, right, this one, the other side, right, delta t minus tau, this was delta t minus 1, fine. So, that is what it is, and then it is an integral of all of those, understood. Okay. So, what we have done so far? We have done the following. If I have a linear system, linear and time invariant system, I am using the linearity property multiple times, I am using the time invariant property also. Okay, I am using all these properties. So, if I have a linear and time invariant system with impulse response h of t, what is h of t? It is a property of the system, right. You purchase the system, shopkeeper told you its impulse response is h of t, beware. Okay. You said okay fine, this h of t is good enough for me. You came back from the market and then you applied x of t over here. What will be the output of such a system? We have just worked out the output. The output is going to be integral x of tau h of t minus tau d tau minus infinity to infinity y of t. Fine. Now, this integral, it is so popular with the EE students that it has a name. We call it not just name, we even have a symbol for it. Okay. We call it the convolution. This operation is called convolution. All right. And it is so popular that we write it as x of t star h of t in shorthand. Okay. So, on the computer star means multiplication, right, on the computer. Star is multiply, right. Here star is not multiply, it is, what is the operation? It is called convolution, and the operation is actually some fancy integral. All right. Now, it turns out that the operators of this, the operands of this operation, which are the operands? X of t and h of t are the two operands. The operands commute. So, they have the commutative property. What do I mean? I mean that integral x of tau h of t minus tau d tau from minus infinity to plus infinity is equal to h of tau x of t minus tau d tau. And why is this? Can you prove this? Substitution will be good enough to prove this. Okay. A simple substitution will do the trick, right. Substitute tau with t minus tau 1, okay. Substitute tau with t minus tau 1, and then d tau is going to be substituted with minus d tau 1, and h of t minus tau is going to be substituted with h of tau is becoming t minus tau 1. So, this is going to be tau will disappear, no, h of t minus t plus tau 1. So, this will become h of tau 1. Huh? And minus infinity? This will go to plus infinity, and plus infinity will go to minus infinity. Fine. So, what do you see? The operators the operands commute. So, x of t star h of t is nothing but h of t star x of t, commutative property. All right. And you are going to soon find out that the other properties, what are they? Distributive, associative, something else is there, all those they all hold. Okay, you can prove in your own free time, because after all it is linear. Achha, achha. So, all those properties also will hold true, right, associative, distributive, but never mind, we do not need, because linearity holds, right. H of t star x of t, if I apply 5 times x of t, I will get 5 times the answer. So, that is also true. So, because of that, all those other properties, associativity, distributive, all of that will also work out for you, right. You do not have to worry too much. Okay. So, convolution is an operator, we use it as an operator. The maths guys of course do not, the EE students think of this as an operator. Okay. We use it so much. Now, why am I talking about all of this? Where are circuits? A circuit is like a system, and for us the circuit is an LTI system, linear and time invariant, and all of these properties are going to hold true. It will also have an impulse response, right, As soon as the circuit is made, it will have an impulse response. And as if you know the impulse response, then whatever input you apply, the output will be that impulse response convolved with the input. Fine. All you need to know is the impulse response. Fine. This is the plan. Okay. Now, what we are going to do is, we are going to apply our inputs as if they are V naught cos omega t plus phi. This is where we started from, right? It started a long time back at t equal to minus infinity, this started. Fine. I am going to go a little, take a little leap over here, and instead of calling it V naught cos omega t plus phi, I am going to add one more term to this and make it plus j times, what is j? J is square root of minus 1. Okay. By the way, this in all EE classes in future, j is you stop calling it iota, do not call it iota anymore, it is j. Okay. For EE students, I interferes with the symbol for current. Okay. We do not write it as I, we are only going to write it as j and j and j, so much that even the software packages like MATLAB, Octave and so on, they know what you are talking about if you type in j. If you type j, it knows that you are talking about square root of minus 1, nothing else. Okay. So, I have thrown in some j sin omega t plus phi over here, right. This j is imaginary, right. This is an imaginary thing. I have added some imaginary thing, right. It is not something real. I hope you are okay that I have added this, right. Many students they say no, we are not okay. How can you add this? But just go with me, take a leap and say that all right, let us add some. It is imaginary after all, it is not something real that I have added. All right. And this whole thing is also e to the power j times omega t plus phi. Fine. Is that okay? Any problem? No problem. Good. So, all our inputs are of this form, or rather let us just take an input, let us just apply one input which is of this particular form. This input is being applied to our system, right. Our system is of course linear and time invariant. What is going to be the response? It has some impulse response h of t, right. The shopkeeper has specified the h of t. How will you write this answer? Convolution of my input with h of t. Okay. So, we are going to write it as integral h of tau v naught e to the power j omega t minus omega tau plus phi d tau, integral from minus infinity to plus infinity. Done? Okay. Now, many things over here are scaling factors, right. Inside the integral, what is varying inside the integral? Tau is varying, right. Otherwise, this j omega t and j phi, okay. Recall that e power this, e power something plus something is e power something into e power something else. Okay. So, these are all factors. So, this is really equal to V naught e power j omega t plus phi times integral is this correct? Fine. Okay, great. Why is this great? Because this entire integral is a constant that depends on what was the h of t of the system sold to you and what is the value of omega, right. Some system you purchased or you manufactured or you made or you assembled, right. That system has some h of t, correct, and omega has a certain value, correct. Now, before you even start the experiment, you could sit at a computer or you could sit with your paper pen and do this computation, what is integral minus infinity to infinity h of tau e power minus j omega tau d tau. You could do this in advance, right. This is not something that you can't do, you could do it. So, this you could pre-compute, this is and it is fixed. Once you have computed this, it is done, it is a constant, it is not going to change after that. Do you see that? This whole thing is fixed, not changing. It could be a complex number, it is probably complex. Is it complex or real? It has e power j omega t. So, it has got to be some complex quantity, right. So, it is okay, it can be complex, but it is still not changing with time, it is fixed, it is a fixed complex quantity, all right. So, this is a fixed complex quantity that you could compute in advance before doing the experiment, before touching the circuit. Shopkeeper tells you this is h of t, you can come back home and you can compute this and get ready. Then you go to the lab and apply x of tau, x of t, right. This is okay, all right. What about V naught? Fixed, this is also a constant. V naught is also a constant, right. So, what is the only thing that is varying with time? Okay. I would go even one step further and I would say that this is equal to V naught times this integral times e power j phi. E power j phi is also a constant, right. It is a complex constant, but it is constant. this whole thing times e power j omega t. Right, all of those are constants. Right, the stuff inside the integral is a constant. It might be inside an integral, but it is still a constant, and then the all the v naught is a constant, e power j times phi is also a constant, okay, because phi is fixed. Right. So, all of these are constants, constant multiplied by constant is also constant. So, all this whole thing is a constant times e power j omega t. Fine. So, this is a super important result that we have worked out. The result is this, that if I have a circuit, arbitrary circuit, it does not matter how complex it is. The circuit has only linear and time invariant components, which are R, L, C, M, and then all the C controlled sources. Okay, dash C dash S. So, VCVS, VCCS, CCVS, CCCS. Fine. And it has some voltage sources, some current sources. Which are all operating at a fixed frequency of omega. Fine. This result says that if I measure now any voltage or any current, any voltage in the circuit, any current through any component, all branch voltages, all branch currents, they are all going to be of the form something, some constant times e to the power j, no minus, j omega t. The only question over here is what is that constant? That depends on what the circuit is, what you measured, right, what was the input, right. That is the only question, what is this constant, we do not know, but it is some constant times e power j omega t. Agreed? Any questions so far? Is this constant real or complex? Which constant? No, this one in brackets. Complex. Why should it be real? We had so many complex numbers multiplying with each other. Huh? There is no reason for it to be real, it is a complex number times e power j omega t. But what do you really measure with a multimeter? Will you measure complex things? E power j omega t, you won't measure that, right? What will you measure? Magnitude? No. No. The real part of it, right. After all, you did not apply the imaginary part of it, I asked you to apply, right. You did not know how to apply the imaginary part, I said throw it in, it is imaginary. So, the imaginary application will result in some imaginary response, right. If you apply an imaginary voltage, you will get an imaginary, I imagine I measured a current, right. But if I apply a real voltage, I should be able to measure a real current, right. The measurement will be the real part of this. Yes. And the real part of this, what is it going to be? Let us say this complex number is A plus j b. And then e power j omega t is what? Cos omega t plus j sin omega t, right. And let us not write this complex number as a plus j b, instead let us write it as r angle theta in the polar form. You know this form? Any complex number? Oh, come on, do I have to do complex numbers with you? No. A plus j b, you can express it as in polar form r angle theta, magnitude and angle. In other words, it is also equal to r times e power j theta. Okay. And this cos omega t plus j sin omega t is nothing but e to the power j omega t, and then I can rewrite this as r times e raised to j omega t plus theta. And therefore, now what will you measure? What is the real part of this? R cos omega t plus theta. This is what you will measure. Fine. Any questions so far? Okay. Have you understood the extremely important result? The extremely important result is that if all my sources are oscillating at an angular frequency of omega, then all my measurements will also oscillate at an angular frequency of omega, omega and only omega. Okay. All voltage measurements, all current measurements, everything will follow some cosine omega t. Okay. No constants, no constant terms. Okay. You will not get some voltage plus cosine omega t. No harmonics. What are harmonics? What are harmonics? Oh no. Of course, it is periodic. What are harmonics? Multiples of omega, right. You will not get anything at multiples of omega. You will get only omega. You will not get cos 2 omega t. You will only get cos omega t. No cos 3 omega t, cos 4 omega t, all of those will not come out. Only cos omega t will come out. Fine? Not fine. Not fine, right? Okay. So, the fundamental theorem for our circuit analysis in sinusoidal steady state so far. By the way, these three assumptions are important, just remind you, right, they are important. One more assumption I forgot to write is that we have an LTI system, that is also an assumption. So, LTI system, all independent sources are oscillating at omega and only omega, because if I have omega 1, omega 2, then all hell will break loose. Okay. You will have beats, we do not want all of that. Okay. Next thing, circuit started at t equal to minus infinity, right, because otherwise my integrals will have some trouble. I will have problems in my integrals, writing those integrals. Okay. The next thing is no self sustaining autonomous oscillators, okay, because if that happens, then it is generating its own omega, we will land into trouble. Okay. So, all these assumptions are important. We understood what is delta of t. What is delta of t? Dirac delta function. It is a two part definition. First part states that the area under the integral is equal to 1. Second part states that it is 0 at all points other than t equal to 0. Okay. Next, what did we do? We broke up any arbitrary x of t, and this was important, right. We broke up any arbitrary x of t into a series of impulses, and we integrated those impulses to get x of t, right. And now, we applied this integral to our LTI system, which had an impulse response of h of t. So, what came out, every time I applied a delta, the response was h, and because the system is LTI, I was able to scale, I was able to time shift, and I was able to add, right. So, the addition, the integral is an addition. So, the addition, the scaling and the time shifting, all of these operations involved assuming that my system was LTI to start with, right. If it had not been LTI, this would not have happened, right. Now, therefore, once it happened, you could also show that they commute, x of tau, h of t minus tau, they commute, and this is also equal to h of tau times x of t minus tau. Straightforward substitution. And then finally, what did we do? We said that our input is V naught e power j omega t plus phi. We applied this input instead of x of t, right, and our output became also, our output also started moving with e power j omega t. So, when my input had e power j omega t, my output also started moving with e power j omega t. So far so good, all right. Now, with this we start with the concept of the phasor. So, the phasor, you see this e power j omega t is coming again and again, it is coming in the input, it is coming in the output. What was my input? My input was V naught e power j omega t into plus phi, V naught e power j phi times e power j omega t. This was my input, correct, and my output is something, some complex number times e power j omega t, right. Every output is going to be some complex number times e power j omega t. Okay. So, everything in the circuit, every voltage, every current has this e power j omega t term, that is multiplying, that not term, factor. Every voltage, every current in my circuit has a factor e power j omega t. Okay. So, what doubly people do is, they say that instead of writing e power j omega t so many times, let us call it a phasor, and we say it is implicit. We know every voltage and every current is going to be multiplied by e power j omega t. I do not want to write it so many times. Okay. So, we are only going to write what is in front. Of the e power j omega t. The scaling constant is all that we are going to write. Fine. This is the idea of phasors, nothing much. Okay. The idea of phasors is nothing much. Let us relax a little bit. Let us not write e power j omega t so many times. right. Let us keep it in mind and move forward. We do not want to write it, we will only work with the scaling constants. Is this acceptable? Acceptable? You also, do you also agree that this scaling constant is the value of that voltage at t equal to 0? Not measured, the value on paper. It is the value of that voltage at t equal to 0. I plug in t equal to 0 into e power j omega t, it becomes 1. Okay? All right. So, what we are going to think of now is the phasor. So, this is the complex plane now. Okay. So, I have a complex number and this complex number, which complex number is this? Let us say it is this one, V naught e power j phi, this one, this is a complex number. Okay. So, I have this complex number and what does e power j omega t do? If I multiply this with e power j omega t, what happens? It rotates by how much? By e power j omega, by an angle e power j omega t, right, and this angle is changing with time. So, this point is basically moving around in a circle, right. You can think of this vector, let us not call it vector now, we are going to call it a phasor. This is the phasor. So, the phasor is rotating with time, right. How is it rotating? Why is it rotating? Because ultimately there is a factor e power j omega t. Okay. But this factor e power j omega t is not something we want to worry about. Let us freeze time at t equal to 0 for now. If I freeze the time at t equal to 0, then what do I get? I get the phasor, that particular vector. Okay. Otherwise, the vector is rotating with time, all the time it is rotating. And guess what? All the voltages, all the currents are also rotating with time. In my circuit, every measured voltage, every measured current is rotating with time, is a complex number that is rotating with time. Is this okay? What is the actual measured value of this? It is the real part of this. So, I take the projection on the real axis and I get the real part, right, that is the actual measured value at any point in time, right. So, if I rotate it by 90 degrees, suppose I measure it at a time such that omega t is 90 degrees, then it is going to be this much, right. So, it is changing with time, fine, but you know all of this, cos omega t is moving around with time, fine. So, this is the notion of the phasor, all right. Now, let us just do a few things. One is phasors obey KVL and KCL. Let us just quickly check. So, suppose I have a phasor. Now, the phasor is a real number, complex number? Complex number. Okay. All phasors are why are they complex? Because no, j omega t is taken out, j phi, it can have a complex part to it, all right, just like I have drawn. what I have drawn is a complex number, not a real number. So, all these phasors are complex numbers, right. At the end of the day they are rotating with time, their starting position t equal to 0 position is that complex number, fine. Okay. Suppose I have a 3 currents, okay. I 1, I 2 and these are all complex numbers, and I 3. What does it mean? What is I 1 actually? Actually it is magnitude of I 1 times e to the power j omega t plus angle of I 1, but this is not what it really is. What is it really? Real part of this. This is actually what it is. Let us put the hat on top to indicate that we are really talking about a complex number over here, right. Later on we will remove the hat, because once you are used to complex numbers we will start removing the hat. For now this is what it is, this is what really I 1 is, okay. And what similarly what is I 2? So, these 3 currents we know KCL, right. The sum of these 3 currents are going to be equal to 0. All right. This is KCL, we know this is KCL, but you have to prove that I 1 complex plus complex I 2 plus complex I 3 is equal to 0. This is what you have to prove. This is given. Anyone brave enough? You want to change T? Let us just do 2 currents, okay. Forget 3 currents, let us just do 2 currents. If I yeah, now who is going to help me? Differentiate. Okay. But omega is coming out. Both are omega, okay, fine. And then what is the next step? Huh. Huh. How is the real part equal? Yeah, but this one I 1 hat plus I 2 hat, it is the only the scaling constant. You are close, but you have not done it. Okay. So, your name is Harsh. So, what Harsh suggested was let us differentiate this thing, differentiate both sides. So, that will give me I 1 hat derivative is 0, I 1 hat is a constant times omega sin omega t plus angle I 1 plus again omega I 2 hat times sin omega t plus I angle I 2 equal to 0, which effectively means that you can remove the omegas. Omega is not equal to 0. So, you can remove it, fine, and now you can multiply it by j. Suppose I multiply it by j, nobody is stopping me. Okay, still fine, and now I add equation 1 with equation 2. Okay, what do I get? I get I 1 times cos omega t plus j sin something, cos plus j sin, which basically means e to the power j omega t plus angle I 1 plus I 2 e power j omega t plus angle I 2 is equal to 0. And what is the next step? Take out, cancel out e power j omega t. What is the next step? I 1 e power j angle I 1 is nothing but I 1, and I 2 e power j angle I 2 is I 2. Is this okay? Hence proved, and you can add many more, as many as you wish. I 1, I 2, I 3, I 4, it is the same, right, whether you have 2 terms over there or n terms over there, it does not matter. Okay. What have we just proved? If the currents obey KCL, then the phasors also obey KCL by themselves. The phasors means just the complex scaling constant, right, those also obey KCL. And if they are not currents, if they are voltages and they add up to 0, if some voltages add up to 0, then they will also obey KVL. The phasors obey KCL and KVL. Fine. Any questions? You have understood? So, what have we proved? We have proved that phasors obey KVL and KCL. All right. And finally, I will throw in the component that I wanted to. What is the voltage? And what is the current in the capacitor? C dV by dt. Fine. These two we already knew from long back. Now, this current and this voltage, the current in case of the inductor and the voltage in case of the capacitor, it is no longer just some random I of t, it is going to be some constant times e to the power j omega t. Okay? Let us not do cos anymore. So, this current is no longer I of t, this current is some capital I times e to the power j omega t, and this voltage is no longer V of t, this voltage is some capital V times e to the power j omega t. In that case, what is going to be the voltage across the inductor? Fine, and that is going to be equal to, do the derivative please, j omega L I fine, which is also equal to j omega L times, how much was this, I of t. Fine. Look at the capacitor. Yeah, do the derivative. Let us start with j. Yeah, j omega c v e to the power j omega t, which is also equal to j omega c times v of t. This is v of t. All right. What it boils down to is something like Ohm's law. It is something very similar to Ohm's law. What was Ohm's law? V is equal to I times R, or it could be I is equal to V by R, okay, either way, right. What have we got over here? V voltage is equal to j omega L times current, all right. So, we call j omega L as the impedance, instead of calling it resistance, we call it the impedance. So, the impedance of an inductor, we call it j omega L, fine. It is just like Ohm's law, and as far as the capacitor is concerned, 1 by j omega c is the impedance. Okay. Again it is like Ohm's law, but the other way around. So, V of t is equal to I of t by j omega c, correct. So, instead of R it is 1 by j omega c. So, the impedance is 1 by j omega c for the capacitor, and it is j omega L for the inductor, fine. Any questions? So, if you think of conductance, right, resistance, conductance is 1 by R, right. Similarly, the instead of calling it conductance, we call it admittance, right, and that is equal to j omega c. Here the admittance is equal to one by j omega L. Fine, it is just like Ohm's law. Instead of resistance we call it impedance, instead of conductance we call it admittance, right. Resistance and impedance are the same basically, just that impedance is real or complex. Impedance is complex, it starts with a j, right. So, j omega L. So, impedance is a complex number, resistance is a real quantity, right. Similarly, admittance is a complex number j omega c, whereas conductance is a real quantity. So, when we have only resistors we have conductance, but when we have R, L, C all these things, then we have admittance and impedance. Fine. Otherwise, it is just like Ohm's law. Fine. Great, because now in the next class you are ready to solve circuits which have R, L and C, general circuits which have R, L and C, right, and you will be using which methods? Mesh method, node voltage method to solve general R, L, C circuits. Fine. Let us stop.